So the way we're going to change the problem, you always analyze these problems by discrete choice, all the discrete choice problems. But if you actually look back in economics a little while, historically, the same problem was analyzed a long time ago, and it was called revealed preference. Okay? So this started with a famous article by Samuelson, and Hal Varian had a bunch of articles on it. And this is going to take off from that. Okay, this is the starting point of that. The difference between what I'm going to do today and what was done, with starting with Samuelson, is they never worried about putting errors in it, disturbances in the thing, because they weren't really doing empirical work at the level that we do today. They didn't have the data sets we have today. They didn't have computers that we have today. So what I'm going to do is put errors in the revealed preference thing, and then show how you estimate given real preference, just revealed preference type arguments. Okay? So it's going to matter the properties of the errors, just like it does in discrete choice. Okay? So it's going to be, we're going to have to pay attention to that. So what you work with now is not really a model, and there is a model, but it isn't, in a sense, it's going to be much more weakly specified than the models you're used to in standard discrete choice. The way it's going to go is the following. It's going to say, I know what the individual chose, and I know some other option that the individual knew that he could have chosen, or it could have chosen, okay, rather than the one it did in fact choose. Okay. At the very least, what I'm going to assume is its expected utility or expected return from the choice the individual made is greater than the expected return from the choice the individual didn't make. So that's revealed preference, okay? And that's all I'm doing, okay? The two things about it, I'm going to have a parametrized model for the utility, okay? So that difference will be positive, okay, for some values of the parameter vector, and not positive for other values of the parameter vector. At the true value of the parameter vector, we think it's positive. Okay, and that's going to be the information content used in estimation. Okay? The problem that's going to arise, and this is what got the econometricians going, which sometimes I'm a fellow traveler, is that if one value of a parameter satisfies an inequality, typically values close to it will also satisfy the inequality. It's an inequality, not an equality. Okay? So we get estimators of sets instead of the set, and the property of the set is we know the true parameter, at least in the limit. The property of the set is we know the true parameter is in that set, and that's all we know. Okay? So it's going to be a weaker form of identification. Formally, it's called partial identification. It's been in the literature, in the econometric literature, actually, for quite a bit. The first time I ever saw it was in a paper by Marshak and Andrews on production functions, the very famous paper. The first paper on simultaneous equations bias was really Marshak and Andrews on production functions. But again, it's only recently has been brought to sort of starting to be used, and the econometrics worked out, okay, in detail. Okay, I'm going to start with an example which is due to a student of mine who's either smart enough or stupid enough, depending on how you look at it, to go join a hedge fund afterwards and make a lot of money. Okay, so his name's Michael Katz, and it was in his thesis. Okay, this was his thesis. Okay, so he takes what is a real classic problem, both in I/O, by the way, and in public finance. I start with this example because the example illustrates very well exactly what's going on in this stuff, okay, and without doing anything formal. So I could start with, for example, this paper by Pakes, Porter, Ho, and Ishii. But then you get to these conditions which are right for Econometrica, but not the right way to explain it to people. Okay, so I'm going to do it this way, okay? So we're going to estimate the cost shoppers assign to going to a supermarket. Okay, to driving to the drive time cost. Okay, it's a problem of big importance for public finance also, and you probably don't know this, but the third biggest expenditure category of people is food. Well, it makes sense, right? There's housing. I don't know if automobiles is greater than food or not. Transportation might be better than food, but it's a big part of the economy. Maybe health. Maybe I've got this wrong. I probably have old data on that. But it's a big part of the economy. The other thing is it influences things like zoning laws. The zoning laws are influenced by you know, the cost of zoning laws are influenced by the cost of driving to supermarkets. The benefits of public transportation programs, you know, BART in Berkeley and the new one they're trying to put in California. Now, it all depends on these costs of transportation time, okay? It's been a problem which has typically been proven very difficult to analyze with standard discrete choice. The reason is the bundle of goods, there are just too many possible bundles of goods. They're every bundle, every choice, every bundle of goods at every supermarket that the guy can drive to. That's just too big a choice set to work with, okay? You're going to see one of the big advantages of the moment inequality approach relative to the standard discrete choice approach is the moment inequality approach, you like large choice sets. It's a help, okay? It's not a hindrance. Is that clear? In standard discrete choice, it's a hindrance, okay? It's a hindrance just because you have to, every time you compute, you have to compute all the probabilities of all these many, many, many choices, okay? And so the more choices, the harder the computational problem. And typically with more choices, you're going to have more parameters to estimate. So it's going to hurt you, okay? Okay, so the way that Michael did this actually is, and this is, you know, straight from his thesis. Had some input by me, but mostly it's his thesis. Is that he's going to assume the following thing. The agent's utilities are additively separable. They're additive functions of an expenditure. So they're additive functions of the following three things. The utility from the basket of goods that the guy bought. Okay, that's one component of utility. And then the disutility for expenditure on that basket of goods. And the disutility for the drive time, for the hassles of drive time. Okay? So his decision vector is going to be, it's going to consist of two things. It's going to be the bundle of goods he bought, which I'm going to call BI, and the store he shopped at, which is SI. Okay? And the utility function is going to be additive. So there's, the utility is going to be, the utility, so Zi are individual characteristics, okay? Di is the decision, okay? The utility is broken down into the utility from the bundle of goods it bought. So each individual, depending on his characteristics, gets a different utility from the same bundle of characteristics, and there's a bunch of bundles, okay? So that's W, Bi, Zi, and theta B, okay? Then there's the expenditure at that store for that bundle, which is E, Bi, Si. I get a free normalization. Everybody remember this? I get a free normalization, okay? So I'm going to normalize the coefficient of expenditure to 1, okay? So the cost of drive time, the next thing is the drive time, dt, drive time, for the individual, SI, to go to store SI when the individual has characteristics Zi, where Zi is where he lives. Among the things in Zi is where he lives, okay? So the only thing that's normalized here so far is E, it's expenditure. I've normalized the coefficient of that to 1. What that means is that the cost of drive time is in terms of dollars, dollar expenditures. Okay. Do I have to tell you anything else? No. Okay, so now let me look back to what you would have to do in a standard discrete choice model for this, okay, to show you why we think about moment inequalities, okay? So there are two forms of the standard discrete choice model that you could use on this, okay? If you're really doing it seriously, okay, you could say there are two approaches. I could assume a standard approach would be full information, okay? So what's the full information say? Each agent knows the prices of all goods at all supermarkets, okay? Pretends he goes to each supermarket, maximizes with respect to the bundle at that, with the prices that chooses a bundle, okay? And then does a maximum over the bundles. Is that clear? So that's what the standard model would say, okay? So if you think of what's going on here, this really has two problems, both a behavioral and a computational problem. First of all, it endows the individual with an incredible amount of information, okay? He knows the prices of each bundle at each store, at each particular product at each store, and then he's able to, and then pretty good computation abilities because he's able to maximize at each one of these stores over this whole bundle and get the right thing, okay? So that's the first thing. Secondly, computationally, it's horrendous, okay? Because, you know, if you thought of it, you would have to go to each store, maximize over the bundle in the store, and if it was fine enough grid of the things you bought, okay, it would be pretty difficult. Okay, and then you have to maximize over the stores, okay, and then estimate from just the maximum over the stores and the optimal bundle. Okay. So that's one way of going about it. It's computationally hard, and it has assumptions that probably aren't believable. Okay. So there's another way of looking at it, which is probably more realistic behaviorally anyway, which says, look, what I'm going to do is in the first period, the agent chooses which store to travel to. And he doesn't have to know everything at the store. He has some perception of what prices and characteristics of the store are, okay? And he chooses which store to go to, okay? Perhaps not with correct expectations, but he has his own perceptions, okay? And the second agent, the agent goes to the store, sees the bundles and the prices perhaps, and chooses, okay? So that's a different behavioral model, okay? And it gets rid of the problem of assuming the behavioral problem in some sense. It gets rid of the problem of assuming the agent knows everything everywhere and always can maximize exactly right. Okay? We got rid of that problem. But for the econometrician, it added a problem. Because I have to be able to specify what the agent's prior distribution was over the stores. Is that clear? And that's precisely the kind of information we never have. Okay, we never ask agents, what was your prior distribution, okay, of prices at Walmart or prices at, okay, or anything else, okay? So it does get rid of the behavioral problem, but it doesn't get rid of, it changes it to a specification problem. How do I specify this prior, okay? And what does it condition on, okay? And it actually makes the computational problem much more difficult. Because now what I have to do is, if you give me a specification for the agent's prior, for every price vector, I have to compute the optimal bundle and then integrate out the expectation to get expected utility. Okay? So it actually makes the problem more difficult from a computational point of view. Okay. So let me say, I don't want to... it's not like this problem hasn't been estimated before. Okay, it's like there's been a lot of work, okay, on these kind of problems. And the way to look at the work that's been done, okay, is they're providing you with descriptive summary statistics. And that I can write down as a discrete choice model, okay? So the reason I'm not doing that, okay, is I actually want to know a structural parameter because I want to do counterfactuals, okay? I want to know what would happen if we built a subway system. Okay? And just what they're going to get from the summary descriptive statistics, which I'll explain in a second, is not that. Okay? It may be a step in getting towards that by projecting stuff down onto observables and making you think, well, this has to be in the right model. Okay? And stuff like that. Okay? And that's a good way to start doing empirical projects, shouldn't get me wrong. But it's not going to get you the structural parameters. Okay? So, I mean, the way this is typically done, has been done, is you group choices into basket of goods somehow, usually by expenditure level. So you say, okay, if people are going to spend this much money, okay, they're going to buy this kind of expenditure. I can see in the data what people bought, that kind of money bought. Is that clear? Then I'm going to have some specification for the basket where I just, for that expenditure level, regress it on observables of some kind, like prices and stuff, your family characteristics and stuff like that. Okay? And then evaluate the possible basket at different stores. So what it will say, here's what you're going to buy. Everybody in this expenditure class buys this, okay, or at least everybody with your ZI in this expenditure class buys this, okay? And what I'm going to do is I'm going to figure out at the various stores that you can shop to in some, reasonable distance around your house, okay, what does that cost there, and what does that cost there, and what does that same thing, and I'm going to choose where you buy. Okay, so that's what goes on. So that's translating it. That's already back into a discrete choice framework. I do the projection. All I have to do to move back to that is I have to make an assumption on the error distribution so I can get to discrete choice. Okay? And I'm just going to project these utilities from buying this bundle at this store, at this expenditure class, down against stuff, and there's going to be a residual. And I'm going to assume that residual has a normal distribution or an extreme value type 2 distribution, whatever you want. Okay? And you go ahead and do standard discrete choice. Okay? So there are two problems with this. Okay, one is the one I already explained. That's the one that really motivated me, which is, it's not a structural parameter. And I'll show you when they do this the kind of numbers they get. And you'll know that it's not a structural parameter, okay, by just looking at the numbers, okay? And you know, then it's not, if you're really just doing this summary statistics stuff, which I firmly believe in, and I always start my research projects doing that, you know, it's not clear when you put something more fancy in it. Like you put random coefficients on the prices, what are you doing? It's no longer a simple summary statistic, okay? So, and it's not the structural model, okay? So what are you estimating? Why would you ever do that? Is that clear? It's not helping you either way, okay? So, okay. So now I'm going to say, let me just say, you got to do something. My general thing is, you shouldn't get me wrong. The people who do, you got to do something. Somebody's going to make decisions on whether we have BART or whether we have an LA subway, okay? And it's not clear that just doing this stuff doesn't do better than the guy with an intuition somewhere sitting in, you know, some office somewhere, who probably doesn't have your education. Do you know? I don't want to belittle it, but it clearly there's wrong. There's a sense in which it doesn't get where we want to go. Okay. So now I'm going to give you the revealed preference analog of this. Okay. So all I'm going to do is I'm going to compare the utility the individual got from the choice the individual made to that of an alternative that I know was feasible to him when he went there, when he made the her or him or it, when they made that choice. Okay? So the real question here, and the most important thing, is what alternative am I going to compare it to? Is that clear? Because, I mean, I said already, there's millions of alternatives out there for this guy, different bundles at different stores. You could do whatever you want. Is that clear? And I could compare any two alternatives. Okay? So the way you choose the alternative is analogous to the sample design problem. If you had your choice of sample among all these samples, okay, which are all the alternatives, which one would you choose? Okay? So it's very clear here. The answer to that, of course, depends on what you're interested in estimating. Okay? So you want to choose an alternative that gives you a very clean look at the thing you're trying to estimate. Okay? So my interest is in analyzing the cost of drive time, or Michael's interest was in analyzing the cost of drive time. So what's the alternative I'm going to do? I'm going to hold the basket constant. I'm going to say, you could have bought this same basket at a different store. Okay? And I'm going to get the difference in utility from buying this basket at this store and this basket at the different store. Is that clear? That's going to difference out the effect of the basket of goods, which is what's causing me the problem, because it's the thing that's multidimensional. Is that clear? And it's the thing that I don't know expectations about and all of this. Okay? Now you can say, okay, well, if he would have went to the other store, he would have bought another basket of goods because there are different prices. Okay? But he chose this store, so in expectation at least, he thought what he could buy at this store was better than what he could buy at that store. And what he could buy at that store has always got to be better than if I force him to buy the bundle he bought at the first store. So by transitivity of preferences, I keep the inequality. Okay? So that's not an issue. Okay? It's just transitivity. Okay. So, so the one I'm going to go first with is he's going to buy exactly the same basket of goods, okay, at a store which is further away from the store, from him, than the store where he bought at. Okay? So that's one option to me. So I'll look for a store that's further away and come back, okay? Okay. So the big advantage of this alternative is if I do that, I'm never going to need to estimate W, which is the complex factor, okay? It's just never going to have to happen. Okay. So two other things you should notice I didn't have to specify the whole choice set. It just doesn't matter. I need one feasible alternative. Okay, and that's often a very difficult thing to do. And two, the alternative choice can differ with different agents. So for every agent, I'm going to look at an alternative that's different. If you went to this store and this store is, farther away from you, that's the alternative. If you went to that store that was, okay, I'm going to look for one that's farther away from that store. So for every I get to choose a different alternative for every agent. That's going to help me. Okay? Okay, so now I'm going to do some algebra, okay, to show you how this works. So I'm going to introduce two things. First of all, I'm going to introduce this expectation operator. this expectation operator is the agent's perceptions. Okay? Is that clear? It has nothing to do with reality. In fact, he could be wrong. Okay, I haven't told you if he's wrong or right. People can make errors. Okay? So this expectation operator is the agent's expectation conditional on what the agent knows when he makes his decision. Okay? And just for notation, instead of carrying around f of xd, or the utility from x and d, and the utility from x and d prime, I'm just going to write always delta f x d d prime. That means the difference, take any function f, the difference between its evaluation at x and d prime will be delta f x d prime. Okay, so that's the notational stuff. So then I can write, the thing is, for every individual, by the way, questions are fine, right? So for every individual's di, I'm going to specify, I've just specified a d prime. That is what my alternative, okay, is my d prime, okay? And it's a function of di and zi. And the only thing I need to ensure about that is it was feasible. When the agent chose what he did choose, it was feasible for him to choose this alternative thing. Okay? Okay. So now I'm going to say my behavioral assumption is with the agent's expectation operator, which again need not be right, okay? He expected the utility from d to be greater than the utility from what he did choose to be greater than the utility from what he didn't choose, which is d prime. Okay? And the expectation is conditional on what the agent knew. This is script JI, mathcal JI, is the agent's information set when he made his decision. Okay, what he's conditioning on. Okay? And so if you write that down, okay, and just do it, the W's difference out because he's buying exactly the same bundle of the two goods. Okay? So remember, the utility function was, where was the utility function? Am I going the wrong way? No. Yeah, this is the utility function. Okay? So if I take the difference between di between di and d prime, where wbi is the same, the w just falls out. Okay? And I'm left with the differences in expenditures and the differences in dive times. Okay? And what I know is that at least an expectation, okay, the agent's expectation is that difference is positive at the true value of theta. Okay? So again, I've not assumed the agent's perceptions on prices are correct. Okay? I will need something, but I won't need that. Okay? And the big advantage of this is so far, and I never will have to, I don't have to specify what the agent's prior is or what he conditions on. That's the specification problem in the other way of doing uncertainty, and I've just gotten rid of that. Okay? So now I'm going to look at the inequalities I get and how I estimate. Okay? So I'm going to look at two different cases. One case is where theta I is constant for everybody. So again, I'm making it simple. Okay? And in fact, in the paper, theta I equals x zi beta time plus an error. Is that clear? And I could put in zi beta here. But what I want to do is say the only determinants of drive time, the cost of drive time, are observable things. Okay, there's no error. That's case one. Okay? It wouldn't matter. I could put in zi beta here, and that wouldn't be a problem. Okay? But it would be a problem put in. Okay, so let's do that for a second. Okay? Let's say theta I equals theta 0. So now here's what I need for this to work. Actually, I need weaker than this, but this is the easiest way to show it. Okay? I need to say that, look, here's my average expenditure difference over people. Okay? I just take the average expenditure. There's a difference in expenditure agent I from di to d prime, which I can compute because I know what bundle he bought, and I can just compute the cost of that bundle at the other store. Okay? And then I'm going to take the average of that over agents. Okay? And what I'm going to assume is the average of the expectations equals the average of the realizations. So people aren't consistently wrong. Is that clear? I need something for a behavioral assumption, and that's it. Actually, I need weaker than that, but for this, I'm going to go with this, okay? Similarly, agent's average expectation of drive time is equal to the empirical average of drive time. Everybody with me? So people can make errors. They just can't be consistent errors. Okay? So P is my notation, P is convergence and probability. Okay? So let's assume that's true. I know that given that theta I equals theta naught for the same theta for everybody, I know that holds for everybody. If I take the average of that equation on the top over people, it's the same as putting in the average of the realizations, because I said the average of the expectations equals the average of the realizations. Okay? So that just says that the average of the things on the right hand, the average of expenditure divided by the average of drive time is less than or equal to the mean theta, that theta that I'm trying to get. Okay? Just take it over. Everybody with me? Okay? So that gives me a lower bound for theta. Is that clear? And my only assumption is that these averages converge to the right thing. Okay? If I would have taken an alternative which was closer to the individual instead of an alternative that was farther away, I would have got an upper bound for theta. You can do it in your free time. Okay? So in fact, what I've got from these things, by just looking at three averages, wait, let me finish. Okay. I get upper and lower bounds for theta. Go ahead. Right. Yeah, so again, no, it will violate this one, but it won't violate the one with theta i's, which I'm getting to next. What you're saying is the ratio of, drive time, okay, to price is different for different people, okay? Okay, so what I'm going to say is, yeah, I'm now going to do that case, okay, and it's going to be fine. Remember, I'm giving you the same bundle of goods at the same store. You should think of that actually as the same store also, the same kind of store. So in the W will be stuff that relates to the kind of store. I will come back to that. But this really is a trade-off. You're trying to hold all of that constant, the type of store, okay, and all of that constant, okay? And you want to look at the trade-off between drive time and expenditure, okay? And I'll show you later that you can actually do tests of that if you've got enough of it. Okay, enough of theta. In fact, I'll show you in a second. Okay? But you're right. I mean, the issue, you'll see, I'll come back to this several times during the talk. The problem with this is the amount of heterogeneity you can allow. Okay? And I will come back to this several times during the talk. Okay? Okay, so that's one case. That case, we start out with theta equal the same for everybody. Let's now say theta is different for everybody. Everybody with me? Okay? So theta I equals theta 0 plus nu I, and I'm going to let theta 0 be the mean. So by construction, the sum of nu I is 0. Okay, that's the definition of theta. Okay? Okay, so the general case would be theta I equals zi beta z plus nu I. So this is exactly what we did in the random coefficients model. Okay? The nu I is the sources that aren't picked up by the z's. Okay? But there's going to be a difference because I don't need to make the same assumptions you have to make in standard discrete choice on the nu I distributions. Is that clear? In the nu I, we then made an assumption on the nu I distribution, and like BLP, we integrated them out with that distribution. Okay? I'm not going to do that here. Okay? Okay. Okay. So in particular, I can always do this and make sure that nu I is uncorrelated with z by construction, by definition of beta I. Okay? But it need not be mean independent of z, and it might not be independent of z. Just the correlation is 0. Okay, so all of those things that you're putting on when you do discrete choice, those are assumptions. Okay? Okay. So now the specification looks at least like the same specification as last lecture. Actually, I need less on the nu i's now. Okay? Okay, so now what I'm going to do is I'm going to assume, say the guy knew drive time, so it was in his information set. So I can condition on drive time. That's something which, maybe it varies a little bit, but it's pretty well known to the guy. Okay? So now my inequality is this. The expected expenditure change minus theta 0 plus nu I now. Delta D has got to be greater than 0. Okay, so the only difference between this and last time is now instead of theta 0 there, it's theta 0 plus nu I. Everybody with me? Okay. So now divide by delta t. Remember, delta t is negative, so it's going to change the sign of the inequalities. It's the difference between the drive time to the store I went to and the drive time that's farther away. Okay? So I'm going to change the inequalities, okay? And I'm going to get the inequality, this inequality here. Okay? So I've done nothing except for divide. Is that clear? Okay. So now I'm going to assume again that I know dt, okay, and the average of the expenditures are right. Okay, that is the perceived expected expenditure, is that clear, is on average right. So you can make errors, but the probabilities converge, the means converge to the right thing. Okay? So then I can average this this right-hand side, okay, and it has to be less than or equal to the average of the right-hand side. The average of the right-hand side is theta 0 by definition. Okay? So now I've got my lower bound for theta bar, and now I've allowed for heterogeneity. Okay? And I haven't had any specification for its form. Is that clear? And if I did the other way, if I got somebody closer to me, I'd get a theta upper bar, and I'd get 2 bounds. Okay? So you should keep in mind a couple of things about this, because it's going to determine when this is particularly useful. Okay? I didn't have to assume anything on the new i's. The new i's could be correlated with x's or z's. It just doesn't matter. Okay? For this. So when you do discrete choice, some people do it non-parametrically. Okay? But they always assume that the new i is independent of the x's and the z's. Okay? So when is that likely to be important? Okay? So think of buying a durable good, like a car, okay, and only now we're going to say it's durable. We're really going to worry about it. Okay? Last hour and a half it wasn't durable, but it became durable in this hour and a half. I'm magic. I'm good at sort of determining what the world looks like. It reminds me, there's certain economists that I think are like this, which is like, I won't tell you who I said this joke to, but it's like, the world isn't like the model, change the world. Which is what I just did. In the thing where you're doing the electrical appliances or an air conditioner, okay, there's usually also an efficiency. There's an amount you're going to use it, and there's an efficiency character. So it's miles per gallon or it's BTUs per air conditioner, okay? And there's a new I on something like, the quality of the air conditioner, okay? And there's going to be also in there, how much you use the air conditioner or where you live, Florida, for that matter, okay? You're assuming that your distribution for the new I, which is the quality of the air conditioner, is independent of how important the air conditioner is for me, whether you live in Florida or not. Is that clear? That's a lousy assumption. Is that clear? We didn't make that assumption here. Okay? There was no need to assume anything about the distribution, the relationship of nu I to z or x. It's a mean that we're getting. Okay? So that's one place where this is actually very useful. So the flip side of this, okay, is so far, okay, I've only gotten you the mean of nu I and not the whole distribution. Is that clear? Okay. And I'd actually have to make some set of assumptions to get more than the mean. Okay. And I haven't told you any of those yet. Okay. I'll tell you what Michael does in a second. Okay. Okay. So 2 other points. Case 1 versus case 2. Again, case 1 was the case where there was no unobserved heterogeneity in the coefficient. And case 2 is when there is totally free unobserved heterogeneity in the coefficient. So what's the difference between them? Okay? Well, the difference between them is in case 1, I get the estimates by a ratio of 2 means. Okay, that's the estimate up on the board. Case 2, the only difference is I get the estimate by, whoops, why am I doing this? I get the estimate by the mean of the ratio instead of the ratio of the means. That's the only difference. These are trivially easy to compute, right? You just take the means. One time it's the ratio of the means. The other time it's the mean of the ratios. Okay? Okay. If the unobservable, wait a second. If the unobserved nu i's really are correlated with something else in the model, okay, then these two things should differ, because the first one will be wrong. Okay? And if there's unobserved new i's which are important and are correlated with things, okay, then you should see the first thing is wrong and the second thing should be different. If the new I isn't important or isn't correlated with things, okay, they should be the same. Pam, you had a question? Okay. Okay, so here's the empirical results. It was done with the Nielsen home scan panel. This is the same home scan panel that we talked about before. Michael also, everybody should do this, and I force my students to do this, is you compare it to the best thing available before you did this, okay, just to see what was happening. Okay, so what he did is he did what everybody else was doing, was he did a multinomial model where he divides the observations into expenditure classes. I can't remember what the classes were. There were about 16 of them, I think. Okay, and then uses a typical expenditure bundle for that class to form the expenditure level. So, you know, there's meats and and then you find a typical expenditure in that class, and you find the price of that expenditure, okay, at different supermarkets. Okay? And then, so that's my price, that's my expenditure bundle or my price, okay? And the other X's he puts in the model are drive time, store characteristics, and individual characteristics. Some interact, a lot of them, 40 or 60 of them, I can't remember. It's a big panel, okay? Okay. So there's problems with this, right? Because what's going on is you might expect that first of all, there's probably an error in price. This is not the relevant price for the individual. The relevant price for the individual is the price for the basket it bought. Is that clear? And you expect an individual to go to the stores where the things it bought are relatively cheap. Okay? So you expect the error in price to be correlated with what the error in, okay? It assumes the agent knew the goods were available in the store and their prices exactly when they decided which store to go to. So this is a full information model type thing, okay? And it doesn't allow for heterogeneity in the effects of drive time at all, okay? I could allow for heterogeneity in the effects of drive time, okay, but then I'd have to do a specification for the distribution of the drive time heterogeneity, okay? And we're worried about it being correlated with other things, okay? Where you live and stuff like that. Okay, where you live, you know, is correlated with your income and stuff like that. So these are the summary statistics that I talked about before. That's what discrete choice is doing in this complicated model. It's giving you a set of summary statistics. Okay? So the way he does it, he allows the drive time coefficient to vary with household characteristics. Okay? And then he focuses on the average of the drive time coefficients for median characteristics. Okay, because he has a lot of different things, okay, different stuff. So there's about 40 coefficients, including things like chain dummies, Whole Foods, Walmart. So we look for this for a Whole Foods store that's farther away from you, okay? Chain outlet size, employees, amenities, all sorts of stuff, okay? Are these 40 coefficients that he's estimating along with the W's, okay? And so he estimated the multinomial model, and his mean cost of drive time per hour was $240. Okay, so you know this was Massachusetts. So even in Massachusetts, a relatively wealthy state, you'd worry about that. I mean, the median wage in Massachusetts was at the time $17 an hour. Okay, so you know people really don't like driving. You know, it's like 4 days of work they're willing to give up for an hour of driving. Okay, it's something on that order of magnitude. Okay. And several coefficients have the wrong time. You don't like to be near a subway sign. You don't like to be near a subway stop and stuff like that. Okay? So the inequality estimators were obtained from the following. So to do the inequality estimate, I have to specify the alternatives. Okay? So he took 4 alternatives. One store that was farther away, one store that was closer to, one store whose prices were typically higher, and one store whose prices were typically lower. Okay, that is, you did an average bundle and you figured out the prices of the various things, okay? And he also interacted it with instruments. So these inequalities, okay, they're not the only inequalities I could get, conditional, because I have this expectation. So the expectation of the difference conditional on JI, and his information set is 0. So any function, any positive valued function of the things that the guy knew when he made his decision could hit this inequality. It should still be positive. You multiply a positive number by a positive number, you get another positive number. Is that clear? So, so what you need for an instrument is it has to be known to the agent when he made his decision. Okay, so he could condition on it when he made his decision. Okay, it has to be uncorrelated with the unobservable that the agent. If there's an unobservable that the agent knows, it has to be uncorrelated with it. Okay, and it has to be non-negative. You have to transform it somehow so it's non-negative. Because you multiply a positive number by a negative number, you get a negative number. Okay, and we want to keep everything positive. Okay. So this is just saying what you need. If you have those conditions for this one, and you multiply each agent's ratio by h of xi, you still get an inequality. Is that clear? Because hx times nu I is mean 0. So it'll converge to 0, okay? And I'll get hx times theta. Whoops, and I should have had hx in the denominator as well as in the... Okay, I made an error. There's a typo here. Okay, but it modulus the typo, I get a lower bound, okay, and now we get an upper bound. So, you go ahead. That's already in the model. I said he has 40 other... I don't remember what instruments he used. I got to admit, I don't remember what instruments he used. They seemed okay to everybody on the market, so that wasn't a problem. I really don't know. I can't remember. But it's the same issues that you always have with instruments. I mean, it's easier actually. So if you were doing, actually, it's sort of important. One of the real problems with discrete choice, and I'll get back to this, is it can't handle errors in right-hand side variables. Okay. So that's the problem with the expectational stuff as well, okay? We'll come back to this in a second. This can handle errors in right-hand side variables because all you're really doing is you're averaging, okay? And as long as the error averages to 0, so when can't you handle an error, okay? When the error enters into a nonlinear function and I have to integrate out the error and I don't know the whole distribution of the error, okay? I've changed this so that all the functions that I'm doing, it's discrete choice, but all the functions that I'm averaging out are linear. Okay? So I've gotten rid of that problem. So you're back to exactly, this is discrete choice, but you're back to the instrument problem in linear problems. Okay? So it's exactly the instrument problem that you know that's dear to your heart and you learned in undergraduate and graduate school. Okay? It has to be in the agent's information set, and then it has to be uncorrelated with the error term. Is that clear? That's what you need, okay? So we can evaluate it, and I really don't remember what Michael did, but that's what you need, okay? You can't hurt you. I mean, so it benefits me because when I have more choices, I can do the sample design part easier. I can find a choice which just differences out the right thing and keeps everything else the same. That's the only place it helps me. Okay? Okay. So when Katz did this, okay, he ended up getting, so it should be a set, right, in principle, if you got the specification right. If one theta satisfies them all, probably more than one theta satisfies them all. In fact, he didn't get a set, he got a point. Okay? So, the bounds intersected. One went on one side and one went on the other side. That's when you get a point. You'll see, I'm going to go over estimation right now, how you do this, okay? Let me say right now, when you get a point, okay, when you have many inequalities, there's good reasons to expect you get a point instead of a set, even if the truth is a set. So let me tell you why, and then I'll come back to it. So just think of you're estimating one parameter, okay? And say I have many inequalities. So I have many upper bounds and many lower bounds for that parameter. Is that clear? Because I have one for each of these hx's that I put up there, okay? So I put up a bunch of hx's. Whoops. Where was that? There we are. If I put up a bunch of hx's like that, everybody with me? Okay. I have a bunch of inequalities for a lower bound. Okay. And what the computer is going to do is you're going to ask it for the greatest lower bound, because I want the smallest set, so I'm going to take the greatest of those. And then I'm going to look for an upper bound. I got many inequalities for the upper bound, and I'm going to take the least upper bound, because there's many of those, and I want to get the smallest interval I can. Okay? So in infinite samples, that would be the right thing to do. Okay? But in finite samples, these are means. Okay? And means have a normal distribution. Okay, so in finite samples, the right way to think is they have a normal distribution. Okay, and if I take the least upper bound, I'm going to get a bias to the left, because I'm taking the smallest one, and the smallest one, on average, okay, will have a negative realization around the mean. Okay, so you're going to push it to one side, and if you do it with the upper bound, you take the maximum upper bound. Okay, on average, you're going to get a positive bias for the maximum, because you're taking the biggest of the upper bound. The biggest will have a positive bias. So they can easily cross. Is that clear? Just go to the computer and do this with, the right model, okay, and have 5 or 6, and then do it with normal sample size, they'll cross. Okay? You can prove that they'll cross with enough inequalities. Okay, they have to, because it's normal and they have full support. Okay? So there's a real question of how I distinguish between, of course, they could also cross because the model's wrong. Okay? So there's a real problem of distinguishing why they cross. Do they cross because it's sampling error of this form, or is it because the model's wrong? So I'm going to show you how to fix that in a second, how to test for that in a second. The reason for this introduction now is that Michael actually found points. Okay? So I had to explain why he finds points. Okay? So he did the two ways, and when he did theta I equals theta naught, so everybody gets the same way, he gets $4 an hour. So that's the ratio of the means. When he does the means of the ratios, the average was $14 an hour, a little bit less than the median wage in Massachusetts. So people, would prefer to drive around with their kid in the car than maybe they would, at least on average. Okay, they'd prefer it a little bit more than going to work for an hour, but they don't like driving very much. Okay, so. So, what he did then is he went and did all these counterfactuals, which I'm not going to go over, which what he did is for every class of people, for every set of Zs and Xs, he then put in the median, okay, and then found out the impact of zoning laws and stuff like that across the thing, okay? So I'm not going to do that. Okay. But now I hope I've given you enough so that you are at least a little bit interested. So what I'm going to do now is I'm going to tell you how you estimate things subject to sets. At least I'm going to give you an overview of that. And then I'm going to go back and compare the assumptions under the revealed preference approach to the assumptions under the standard discrete choice approach. Okay, once more to leave you at the end with, okay? I'll also tell you, what we don't know, okay, which is a lot. Okay, so first of all, let me introduce you to estimation and testing. Okay, so this is not really my work. It's this part of it. It's the first paper really on this was Cherniszuk, Hong, and Tamer, first modern paper in Econometrica, and there's more than I'm going to do here is in the Andrews and Soares articles. There's an Andrews and Gallagher there's a lot of articles, and some of them are cited here that are doing this. This is what Econometrics did for a living for the last couple of years. Okay, so all I really have is I have differences in utility from different choices, and maybe I have some instruments. So at Michael's case, this was a vector of 4 differences, different prices and different distances. Okay, and then he used these instruments. So the Kronecker product operator just expands it. So it says this whole set of instruments is against this moment, and then this whole same set of instruments against this one, and so on. And what it's doing is, so it's really just a bunch of moments. Okay, and what we know about those moments, what theory tells us about those moments, is that those moments are greater than 0 at theta equals theta naught. Okay? Okay. So I think the thing that you have to be very important about, the model doesn't tell you for the true theta they're more greater than 0 than the other one. That bigger, more greater than 0 is better than less greater than 0. It doesn't tell you that. It says, I don't really distinguish between thetas that make it bigger than 0. All I know is that theta is bigger than 0, that the moment is greater than 0. Every theta brings you to a different moment value, okay? The model doesn't say if I have a theta, it brings me to a very positive thing, that's a good thing. It doesn't say that at all. It just says all I know is that at the true theta naught, it's positive. Okay? That's the big difference, okay? So here's my notation. So I'm just going to take the averages. MPN theta is the average over the population, in the sample. PN is empirical process. But PN is just the distribution of individuals, so it's just 1 over n on each individual. And there's a variance, which is sigma PN of these moments across individuals, okay? And then in the population at large, at every theta, there'll also be a moment in the true population, if I had it, and a true variance. And what we know is that at the true theta naught, the true population is positive of these moments, okay? And so the theta zeros, the theta values that satisfy that are all acceptable, okay? So that's called the identified set by econometricians, okay? Because we can't distinguish between them. They're all equally good, okay? Okay. For now, I'm going to go through the estimator, but just for notational simplicity, I'm going to assume that the variance covariance is the identity matrix, okay? So if you want it to be more efficient than what I'm going to do, what you would do is divide each moment by an estimate of its variance and then do the same thing again that I'm doing, okay? But that just complicates the notation. It doesn't change anything else. Okay. Okay, so again, all I want to do is I want to choose the theta that penalizes negative values of these moments. Is that clear? So I'm going to introduce this operator, f minus, which for any function f just takes the negative part. So if f is positive, I give that number 0. Is that clear? If that moment is positive, I give it 0. Okay? And if that moment is negative, I keep it. Is that clear? So I do this for every moment in the moments that I'm trying to estimate. I now have these moments, okay, which are right here. Okay? For every theta, what I do is I look at this moment, and if it's positive, I set it to 0. And if it's negative, I keep it. Is that clear? Okay. Okay. And then I find the values that minimize the sum of squares of the negative part of the moments. This is just the sum of squares. Okay, it's the standard Euclidean norm. Okay? So I'm going to find the value that minimizes the negative part of the moments. Everybody with me? Okay. So there's two possibilities. One is it's a set of values. Is that clear? There's a set of values that set them all to 0. Okay? So if there's one that sets them all to 0, it's very likely that there's going to be many that are set them all together there. Okay? The other possibility is none of them set them to 0. Is that clear? So that's Katz's case. Okay? And then you get the point that minimizes this, just like you do in standard estimation. Okay. Okay, so that tells you how to estimate. Okay? There are lots of papers that give convergence to this, in the appropriate norm to the true theta 0. If the model is correct, this estimator will converge to the true theta 0 set up there in any norm you want, and any suitable norm. Has to be, it's two sets, so you've got to worry about the norm a little bit. Okay, so that's not an issue. So what I want is now measures of precision. Now this is where things get a little bit more complicated than usual. It's really not complicated, it's really very simple, but it's different from what you know, or different from what you got taught in undergraduate school, okay? So there are different notions of precision here, okay? Remember, I have a set estimator, okay? So I have to have a notion of precision. For example, I could give you a set that I know covers the true set, the whole true set, with probability 95%. So that's a confidence set for a set. Okay? That's one notion of precision. Okay? Another notion of precision would be, I'm going to give you a set that covers the true point estimate with probability 0.95. That is, 95% of the times I draw a sample, I'll cover the thing. I'll cover the true theta naught, okay? So that's going to end up being another notion, a different set, okay? And it's another notion of consistency. And then there's yet a third notion of consistency is I might want to look in a particular dimension. So what do we do typically when you do econometrics and you publish a paper? You give a confidence interval for each parameter, or a standard error for each parameter. Is that clear? So I might want to do that too. okay? So I might want to say, look, I'm going to give you a confidence interval for each parameter. So if this, there's, you know, I will cover that parameter with 95% confidence, okay? I'm not going to do that today. That's in PPHI. The one I'm going to do today, it's the easiest one, and actually, it's probably the best one in many ways, except when there's a huge dimensional theta, and then it's not hard. It's hard to calculate. So I'll show you why in a second, okay? So, and there are, let me just say, there are many ways. I'm going to give you one that works, okay? It's not the efficient one, okay? There are better ways of doing this, okay? But it's the easiest one to explain to you guys, okay? And the better ways are just simple add-ons to this. They're just bells and whistles, okay? So the better, if you're interested in doing it in a better way, you can look at this Guggenberger and Andrews paper. It has, I don't know, at that time when it published it, it had everything in it. Okay, it probably doesn't have it anymore. Yeah, shoot.
So far you haven't said anything about the size of that confidence interval that we cover with 95%. So it could be massive or it could be small.
Right. So let me just say, even, you know, I was going to say this at the end, but let me say it now, okay? So if you have a problem where you think an adequate approximation is gotten by standard discrete choice, in a way you're always going to do better because you get point estimates. And all I can do is get you maybe a narrow interval, maybe, okay? So the trade-off isn't that. The trade-off is the behavioral assumptions, okay? Because in the discrete choice stuff, you're making very strong assumptions as you go along, and this weakens them, okay? And, you know, whether, you know, the size of the confidence, well, it depends on how sharp, you know, your inequality. I mean, that's the sample design question again. You're back to, but what I like about it, by the way, is it's economics now. It's not statistics, okay? It's what's feasible for the different people. What can I think through that will allow me to pin down a parameter, okay? But that's right, what you're saying. Okay. So I'm going to tell you how to get confidence sets for the point theta 0. So again, I think this is probably the most sensible way of looking at it if you have a small dimensional problem, okay? You might also want it interval by interval, okay? But so this is the way it proceeds. It's really very simple. I'm going to look, in principle, I'm going to look at each possible value of theta in this space, okay? And I'm going to compute whether I can accept the null that theta, okay, makes all the moments positive. I'm just going to do it point-wise, okay? At every point in the space, I'm going to look, and I'm going to do that computation. That works out to be a very simple computation. I'll do it for you now, okay? So I'm going to look, okay, so what do I have to do? Why is this problematic? Okay, it's problematic because I have to divide, I have to look at each point. I can't look at each point in a continuum. Okay, so I'm going to have to divide the space into some kind of grid. Is that clear? And to get any kind of precision, the grid should be, you know, pretty precise. And if I have 100 variables to estimate, pretty precise grids means, you know, if there's 10 points in the grid for theta 1 and there's 100 thetas, it's 10 to 100 grid points to evaluate. Okay, that's where the problem of this comes in. Is that clear? It grows exponentially. Okay? But if you have a small problem, this is a good way to proceed. Okay. So how do I find out whether I would accept a value of theta p or not? So theta p are the thetas in this grid. I've somehow divided the grid, okay, and the theta p's are the thetas in this grid. So what's the intuition? Okay, the intuition is very clear. For me to accept that, the norm of m theta pp and the norm of the moments when evaluated at that theta must be within sampling error of 0. Is that, you know, because if it is within sampling error of 0, I could have accepted it. Okay? Now I know the moment, okay, the true moment distributes, all of these moments are going to distribute normally with a particular variance, okay? It works out, let me just say, what's the problem here? I should have started with this. The limit distribution of this truncated mean, at this vector of truncated means, okay, is not standard. There's no analytic form for it. Okay, I want to find out the variance of m theta pn and see if it's close enough to 0. Is that clear? That's what I want to do. Okay? But I don't have a distribution for m. Okay? Because it's not, it's this truncated thing that looks funny. Okay? So what I got to do is I got to find a way of simulating that distribution. Is that clear? Okay. I know the variance of m theta. I'm going to keep it fixed. It's a consistent estimate of the variance of that theta. Okay. But I don't really know the mean. Okay. I want to simulate from something. Okay. And all I know. Okay. So I want to. But what I'm going to do is I'm going to assume that the mean was really 0 for a second. Okay. Say the mean of m theta pn was 0, point-wise. Every moment was 0. Okay. I'm going to ask the question: if every moment was 0, what would be the critical value? That's easy to do. What I do is I take random draws from a normal with a mean of 0 and the variance covariance there. Okay. I'm going to call those random draws m twiggle. Okay. That's just just standard norm. Just draw from a normal from the computer. Okay. With that variance and that mean 0. And I'm going to evaluate if I got random draws like that, what would be the value of that? Is that clear? Okay. So, and then I'm going to find out what's the critical value of that statistic. 95% of the time, that statistic is less than something. Is that clear? Then I'm going to go back to the data. I'm going to say, what was the value in the data at theta p? Is it greater than that critical value? Okay. If it's greater than that critical value, it's not within sampling error of 0 if the true mean was 0. Everybody with me? What's going on? Okay. Now, it's true that all that reasoning was based on the true mean being 0. Is that clear? But you can show that if the true mean is any positive number, okay, the critical value will be less than that, because you'll just be adding something to the moment all the time, and to get to 0 will be easier. Is that clear? So now I have a test which is based on the extreme point. So I've satisfied the criteria that I will, for any true mean, okay, which is greater than or equal to 0, okay, I will have rejected with probability less than 0.05. Okay, so that's the logic. Okay, now there are ways to fix this up. Okay, and the ways to fix this up all have to do with adding positive numbers to the m theta. Instead of doing from a 0 distribution, doing from some other distribution, because that'll be more powerful because you'll reject more. Okay, and I'm not going to go. That's what this Guggenberger and that's all they're doing. Okay. Okay. So that's how you do inference in this thing. So if you do this at every point, the points that you can accept are your estimated identified set. The points that you can't accept are thrown out of the identified set. You want a confidence interval for a particular parameter. You go to this identified set. You look for the lowest value of the parameter that's in the identified set and the highest value of the parameter for the identified set. That's your confidence interval. Everybody with me? Okay. So there's a lot more to learn about the statistics of this stuff, but that's the basics. Okay? And it's pretty easy to know. Okay? So now I want to go back to my moment inequalities versus standard discrete choice. Aviv, I'm going to give you your extra 15 minutes, it looks like. Okay. I'm going to go to moment inequalities, and I want to compare these two ways of doing things. Okay, just to leave you, and to tell you also what to reinforce the problems with them. So let me just say, the limits of the moment inequality methods are really still being explored. There's an active area of research going on now on this. Okay. So the big advantage is it typically requires weaker behavioral assumptions than the discrete choice model. So I don't need to assume full information. People can have expectations. Okay, the expectations can be wrong, just not wrong on average. Okay, I can have models with uncertainty without specifying prior probabilities. That's the important point, because we can still do that with discrete choice. But you would have to specify what the agent knew, so what you condition your prior probability is, and what the probability is conditioned on what the agent knew. And those are the kind of things that we really don't know a hell of a lot about. Okay? Okay. The thing I didn't emphasize but came up in one of the questions was, and it's important in many applications, especially this work I'm doing with Kate Ho, is that the moment inequality only uses averages, so mean zero errors in the right-hand side variables don't matter. Okay, at least they don't affect consistency. Okay, And in discrete choice, that's an extremely difficult problem. Okay, it works out to be an extremely difficult problem. It's not really solved yet, and mathematically, it's an intractable problem. It's called Friedholm equations of the third kind, or something like that. It's a really difficult mathematical problem. Okay. And the third thing, though, and this has its pros and cons, is it doesn't require specification of the whole choice set. Okay? When you do standard discrete choice, you have to specify the whole choice set. Okay. The biggest con about this goes back to Pam's question, okay, which is it has a limited ability to handle variables that the agent does not know when it makes its decision. So an unobservable that the agent did know, when he made it. An unobservable that the agent didn't know when he made his decision is just going to be averaged out. But if the agent did know it, okay, and it's correlated with things, we're in trouble, okay? So we put some, you can do some things, okay? And indeed, in this particular example, I showed you two of the things you can do, okay? One of the things you can do is you can choose the alternative to difference out the unobservable. And the unobservable in this case is the utility from buying buying any bundle of goods. That's one source of unobservable. And what we did is we worked out an alternative which killed it. Is that clear? So that's one thing you can do, okay? The other thing you can do, in the second case, we had a new I, and the new I stayed there after we differenced, okay? Why were we able to get over the new I? Because we said, look, we're going to go after the mean, and I'm going to get a linear function in new I, okay, for every person in the sample, okay? If it's a linear function of new I for every person in the sample, I'm going to average them out and get to the mean. Is that clear? Okay. You have to be very careful here. You can't drop out people. It can be a different alternative for every individual. That's fine. But there has to be an alternative with the new I in it for every individual. Otherwise, you don't get the population mean. You get a selected mean. You get the sample selection problem back. Is that clear? Okay. So those are the two ways we did it in this one. I want to go now to a more general model and tell you what would happen in a more general model. Okay, so the more general model is the agent's is going to maximize expected utility. Okay, and the only difference between this model and the model I put on the board and worked with is now I'm going to put in an epsilon IS, a store-specific epsilon that the agent knew when the agent made its decision. These are expectations now. That the agent knew when the agent made its decision. Is that clear? But I don't observe. Okay? Okay. So this would be a model that we would probably all bite into, because it has the theta I, and it has this, and it has difference, and you can have any difference here you want. So all I'm doing is I'm saying, I'm going to normalize each individual. I get a normalization that's free for every individual. Okay? That's what the cardinality does. Okay? And I just have an expectation, so I'm going to make that 1, okay? And I'm saying this can be totally free, okay? There's a theta I, so each individual can have his own drive time coefficient, and in addition, each individual can have an epsilon IS that he knew about when he made his decision and I didn't. Is that clear? So that's the model I think we'd all like to work with, let me just say, okay? And the question is, where are we on it? So again, a tilde over a variable here is a random variable, which is even random to the agent, because the agent doesn't know everything. And so the expenditure and the bundle he'll buy are unknown to him when he makes his decision. Okay? So there are now 3 errors in this model. Okay? There's the difference between the W we actually observe, or what the bundle the guy actually bought, and his expectations. There's the difference between his expenditures that we actually observe, which is what he actually bought, and his expectations. And then there are these errors. The epsilon choice model, you're shutting down these 2 errors. You're saying they don't exist. Okay? And then you're assuming that epsilon IS is normal or logit or whatever you're assuming. Is that clear? In Michael's model, what he did is he shut down the epsilon IS. Is that clear? And assume these and this, and the distribution of this were free. Okay? That's the trade-off that's going on. Okay? So we'd like a model where you could do both. And the answer to this is there are models like that now. There are 2 sets that I know of, and there probably are more that I don't know of. They're not published yet, and people are not letting them out yet, just quite yet, because people don't know exactly how much bigger the bounds get. It's your question, and actually I'm playing with that right now. So I hate to give you things, okay? It's a different estimating equation. It's not just these moments, okay? So I hate to give you things until I know something about it, but if you sort of keep tuned, there's this paper by Dick Stane and Morales, and there's the paper by Jack and I, which will be coming out soon. They'll tell you how to do it that way. But right now the status is the other one. You get these 2 choices. You either shut these 2 down or you shut the other one down. Okay, that's what's going on.